Welcome to this problem walkthrough. In this session, we will explore problem number 1338, titled Reduce Array Size to the Half. We'll analyze the problem statement, discuss the approaches to solve it, and break down the solution. Let's dive in. In this problem, you are given an integer array called ARR. Your task is to determine the smallest possible size of a set of integers such that removing all occurrences of these integers from the array reduces its size to at least half. Essentially, we want to minimize the number of unique integers we select while ensuring that removing their occurrences shrinks the array size to half or less. For the input, ARR is a list of integers, where its length can range from 1 to 100,000, and each element in the array is also between 1 and 100,000. The output should be a single integer representing the minimum size of the set that achieves this reduction. Let's explore some examples to understand the problem better. In the first example, the input array is 33335555227. This array has 10 elements, so to reduce its size to at least half, we need to remove at least 5 elements. One way to achieve this is by removing all occurrences of the numbers 3 and 5, as they are the most frequent elements in the array. Removing these numbers leaves us with 227, which has only 3 elements, satisfying the condition. Since we selected two numbers, 3 and 5, the minimum set size in this case is 2. Now, consider another example where the input is 777777. Here, the array has 6 elements, and to reduce it to at least half, we need to remove at least 3 elements. By removing all occurrences of the number 7, we are left with an empty array, which has a size of 0. This satisfies the condition as well, and because we only needed to select one unique number, the minimum set size is 1. As a final example, take an array like 1, 9. This array has only 2 elements, so to reduce it to half, we need to remove at least one element. Removing either 1 or 9 leaves an array of size 1. Therefore, the minimum set size in this case is also 1. Let's now think about the constraints and some edge cases. First, if the array contains only one element, such as 1, the output must be 1. This is because removing the single element reduces the array size to 0, which satisfies the requirement. Additionally, if multiple values in the array have the same frequency, any valid combination of elements that achieves the desired reduction is acceptable. For instance, there may be more than one way to minimize the set size in some cases. Finally, since the input size can be as large as 100,000, it's important to consider efficient solutions that handle large arrays without running into performance issues. This ensures that the algorithm scales well even for the upper limit of the constraints. When considering how to approach this problem, we can start with a brute force method. The intuition behind this is straightforward. We would try all possible subsets of integers in the array, remove them, and check if at least half of the elements are eliminated. However, this approach quickly becomes impractical. The reason is that the number of subsets grows exponentially with the number of unique integers, specifically 2 to the power of n, where n is the number of unique integers. This gives us a time complexity of 2 to the power of n, which makes it infeasible for large inputs. On the other hand, a more efficient strategy is the greedy approach. Here, the key insight is to focus on the frequency of integers in the array. Removing numbers with higher frequencies has the largest impact on reducing the array size. By prioritizing these integers and removing them in descending order of frequency, we can achieve the goal of reducing the array size to half, while minimizing the number of integers removed. This greedy approach forms the foundation of the optimized solution for this problem. The optimized strategy begins by counting the frequency of each integer in the array. This can be done efficiently using a hash map, where the keys represent the integers and the values represent their frequencies. This step has a time complexity of n, where n is the size of the array. Next, we extract these frequencies and sort them in descending order. Sorting ensures that we can process the integers with the highest frequencies first, which is critical for the greedy approach. Sorting the frequencies takes k log k time, where k is the number of unique integers. Once the frequencies are sorted, we use a greedy selection process. We iterate through the sorted list, adding up the frequencies until the cumulative total reaches at least half the size of the array. During this process, we also count how many integers were required to reach this total. Finally, the result is simply the number of integers used in this process. This step of iterating through the sorted frequencies takes k time, and it completes the solution efficiently. The key insight here is that by focusing on frequency, we avoid the need to explore all possible subsets of the array. Every approach has its trade-offs, and it's important to consider these when designing a solution. The brute force method, while conceptually simple, is entirely impractical due to its exponential time complexity. On the other hand, the greedy approach is highly efficient, with a time complexity of n plus k log k. Here, n represents the size of the array, and k is the number of unique integers. This approach balances simplicity and performance, making it an excellent choice. An alternative optimization could involve using a priority queue, such as a max heap, to repeatedly extract the highest frequencies. While this reduces the sorting step to O log k per extraction, it adds unnecessary complexity without offering significant performance gains over the simpler sorting method. Ultimately, the greedy approach stands out as the optimal solution for this problem. It ensures correctness while maintaining clarity and efficiency, making it the most practical and elegant choice for reducing the array size to half. To tackle this problem effectively, we need to focus on minimizing the number of unique integers we remove while ensuring that at least half of the total elements in the array are eliminated. For instance, if our input array is 3, 3, 3, 5, 5, 7, 7, the output would be 1 because removing all occurrences of the most frequent number, which is 3, reduces the array size by more than half. The key here is to identify and target the most frequent numbers first, as they have the greatest impact in reaching our goal with minimal removals. The first step is to count the frequency of each integer in the array. Using a hash map or a counter is ideal because it allows us to efficiently track how many times each number appears. For example, in the array 3, 3, 3, 5, 5, 7, 7, the frequency map would be 3, 3, 5, 2, 7, 2. This gives us a clear view of the distribution of numbers. The next step is to sort these frequencies in descending order. By sorting, we can prioritize removing the numbers that appear most frequently first, which is the optimal strategy. For this example, the sorted frequencies would be 3, 2, 2. Sorting ensures that we address the most impactful numbers first, minimizing the total number of unique integers needed to achieve our goal. Now, we proceed by iteratively removing integers with the highest frequencies. We start by initializing two variables, removed_count, which tracks the total number of elements removed, and unique_removed, which counts the number of unique integers removed. As we iterate through the sorted frequency list, we add the current frequency to removed_count and increment unique_removed by 1. At each step, we check if removed_count has reached or exceeded half the size of the array. If so, we stop the iteration early, as our goal has been achieved. For example, in the array 3, 3, 3, 5, 5, 7, 7, the total number of elements is 7, so half is 4. Removing all occurrences of 3 adds 3 to removed_count and increments unique_removed to 1. Next, removing all occurrences of 5 adds 2 to removed_count, making it 5, which meets the condition. At this point, we stop and return unique_removed, which is 2. Once the iteration is complete, the value of unique_removed is returned as the final result. In the example, the result is 2, meaning 2 unique integers were removed to reduce the array size by at least half. This approach is built on several key insights. First, removing integers with the highest frequencies ensures that we reach our target in the fewest possible steps. Sorting the frequencies in descending order is crucial to prioritize these impactful numbers. Finally, the process benefits from early termination, as there's no need to process the entire frequency list once the target is met, which improves efficiency. It's important to consider edge cases to ensure the algorithm is robust. For example, if the array contains all identical elements, such as 1, 1, 1, 1, only one unique integer needs to be removed. On the other hand, if there are no duplicates, as in 1, 2, 3, 4, the number of unique integers to remove is determined directly by half the array size. The algorithm relies on a few critical data structures. A hash map or counter is used to calculate the frequency of each integer, which takes n time. The frequencies are then stored in a list and sorted, which requires O, k log k, time, where k is the number of unique integers. Additionally, simple variables like removed_count and unique_removed are used for tracking progress during the iteration. Analyzing the time complexity, the frequency map is built in O, n, time, where n is the size of the array. Sorting the frequencies takes O, k log k, where k is the number of unique integers. Iterating through the frequency list is O, k. Combining these, the overall time complexity is O, n plus k log k. For space complexity, the hash map requires O, k, space to store frequencies, and the frequency list also takes O, k, space. Therefore, the total space complexity is O, k. These complexities make the algorithm efficient and scalable, even for larger inputs, as the operations focus primarily on the unique integers rather than the entire array. This Python implementation solves the problem of finding the minimum number of unique integers to remove from an array such that at least half of the elements are removed. Here's a detailed explanation of the code. 1. Importing counter from collections. We use the counter class from Python's collections module to efficiently count the frequency of each integer in the input array. 2. Counting frequencies. The counter function takes the input array ARR and returns a dictionary-like object where keys are the unique integers in the array, and values are their respective counts. For example, if ARR equals 333221, the frequency count will be 332211. 3. Sorting frequencies. The values method of the counter object gives us a list of frequencies, e.g., 3, 2, 1, which we then sort in descending order. This ensures that we prioritize removing the most frequently occurring integers first to minimize the set size. For initialization, we initialize two variables, elements_removed and set_size, to 0. Elements_removed will keep track of how many integers have been removed from the array so far, and set_size will count the number of unique integers removed. 5. Target calculation. The goal is to remove at least half the elements from the array. We calculate this target as len, ARR, //2, integer division. 6. Iterating through frequencies, we loop through the sorted list of frequencies. In each iteration, we add the current frequency to elements_removed and increment set_size by 1. This simulates removing all occurrences of a unique integer from the array. 7. Breaking condition. After each iteration, we check if elements_removed has reached or exceeded the target. If it has, we break out of the loop, as we've achieved the goal of removing at least half of the elements. 8. Returning the result. Finally, we return set_size, which represents the minimum number of unique integers that need to be removed to satisfy the condition. This approach is efficient, with a time complexity of O, n log n, where n is the length of the input array. The sorting step dominates the runtime, while the frequency counting and iteration are linear operations. This solution is well suited for the problem's constraints and ensures correctness for all edge cases, including arrays with many duplicates or entirely unique elements. This is the Java implementation of the LeetCode problem: reduce array size to the half. The logic mirrors the Python solution, using a hash map to count frequencies and a priority queue, max heap, to process frequencies in descending order. Key distinctions include explicit type declarations and the usage of Java-specific collections such as hashmap and priority queue. The code efficiently computes the minimum set size required to remove at least half of the array elements. In this example, the input array is 3333555227, and our goal is to reduce the size of the array by removing elements until at least half of the array, which is 5 elements, is removed. We start by calculating the frequency of each unique element, resulting in frequency equals counter 3, 4, 5, 3, 2, 2, 7, 1. This tells us that the number 3 appears 4 times, 5 appears 3 times, and so on. Next, we extract these frequencies and sort them in descending order, giving us frequency_values equals 4, 3, 2, 1. We initialize some variables, elements_removed equals 0, which tracks the total number of elements we've removed so far, set_size equals 0, which tracks the number of unique values we've selected, and target equals 5, which is the minimum number of elements we need to remove. Now, we begin iterating through the frequencies. First, we pick the largest frequency, which is 4. Adding this to elements_removed results in elements_removed equals 4, and we increment set_size to 1. Since elements_removed is still less than the target, we proceed to the next frequency, which is 3. Adding 3 to elements_removed gives us 7, and we increment set_size to 2. At this point, elements_removed is greater than or equal to the target, so we stop the iteration. The result of the first example is that the minimum set size required to reduce the array by at least half is 2. Now, in this second example, the input array is 7, 7, 7, 7, 7, 7. Here, our target is to remove at least 3 elements. Calculating the frequency of the elements, we get frequency equals counter 7, 6, meaning all 6 elements are the same. The sorted frequencies are frequency_values equals 6. We initialize the variables elements_removed equals 0, set_size equals 0, and target equals 3. Since there is only one frequency in the list, we take it in the first iteration. Adding 6 to elements_removed results in elements_removed equals 6, and we increment set_size to 1. Since elements_removed is already greater than or equal to the target, we stop here. The output for this example is that the minimum set size required is 1. In the final example, the input array is 1, 9, 9, 8, 8, 8, 7, 7, 7, 7, and our goal is to remove at least 5 elements. First, we calculate the frequency of each unique element, resulting in frequency equals counter 7, 4, 8, 3, 9, 2, 1, 1. Sorting these frequencies in descending order gives us frequency_values equals 4, 3, 2, 1. We initialize elements_removed equals 0, set_size equals 0, and target equals 5. Starting with the largest frequency, we add 4 to elements_removed, making it 4, and increment set_size to 1. Since elements_removed is still less than the target, we move to the next frequency, which is 3. Adding this to elements_removed gives us 7, and we increment set_size to 2. Now, elements_removed meets the target, so we stop. The output for this example is that the minimum set size required to remove at least half of the array is 2. The time complexity of our solution can be broken down into 3 main steps. First, we calculate the frequency of each element in the array using the counter function from the collections module. This step requires us to iterate through the entire array, resulting in O(n) time complexity. Next, we sort the frequency values in descending order. Since the number of unique elements in the array is k, this sorting step takes k*log k. Finally, we iterate through the sorted frequency list to determine the minimum set size needed to reduce the array size by at least half. This step requires k time in the worst case. When we combine these steps, the overall time complexity becomes O(n) for counting, k*log k for sorting, and k for iterating through the frequencies. When we combine the 3 components, the total time complexity can be expressed as O(n) plus k*log k. Since the number of unique elements k is always less than or equal to n, in the worst case, we can simplify this to O(n*log n). Now, let's analyze the space complexity. The counter object that stores the frequencies of unique elements requires k space, where k is the number of unique elements. Additionally, the sorted frequency list also takes k space. Aside from these, the solution only uses a few scalar variables like elements_removed, set_size, and target, which together require O(1) space. Therefore, the total space complexity is k, and in the worst case, when all elements in the array are unique, this becomes O(n). To better understand the performance, let's consider the best, average, and worst case scenarios. In the best case, if most of the elements in the array are identical, the number of unique elements k is very small. Since sorting and iterating through a small frequency list is efficient, the time complexity approaches O(n). For the average case, k is smaller than n but still significant, so the time complexity remains O(n*log n). In the worst case, when all elements in the array are unique, k equals n, so the time complexity simplifies to O(n plus n*log n, which is written as O(n*log n). For comparison, a naive approach that generates all subsets of unique elements would have an exponential time complexity of O(2 to the power of k*n, which becomes computationally infeasible as k grows. Our solution avoids this by focusing on frequencies and sorting, ensuring that we handle the largest contributions to the reduction first. This makes the approach both efficient and practical. In conclusion, this solution strikes an excellent balance between time and space efficiency. With a time complexity of O(n*log n and a space complexity of O(n), in the worst case, it is well suited for handling large inputs. By leveraging the frequency of elements and sorting, the algorithm avoids the inefficiencies of a naive approach, making it both optimal and scalable. This efficiency ensures that the problem of reducing the array size to half can be solved quickly and effectively, even for larger datasets. Here are some common mistakes to watch out for when solving this problem. First, incorrect subset generation can be a major pitfall. Generating all possible subsets without optimized methods like bit masking or recursion is inefficient, especially as the input size grows. Since the total number of subsets for an array of size n is 2 to the power of n, exponential growth can quickly overwhelm computational resources. Next, improper stopping conditions can lead to incorrect results. It's essential to stop the algorithm as soon as at least half the elements have been removed, rather than continuing unnecessarily. Additionally, ignoring edge cases can result in unexpected behaviors. Arrays with duplicate values, arrays of size 1, or arrays where all elements are identical need special attention during testing to ensure your solution handles these scenarios correctly. Overlooking optimization opportunities is another common issue. If you rely solely on brute force, you may miss out on efficient techniques like greedy algorithms or frequency-based methods. Finally, be cautious with sorting assumptions. Sorting the array directly doesn't always align with the problem requirements. For instance, in this problem, the focus should be on frequency of elements rather than their values. Make sure your approach reflects the true priorities of the task. To excel in interviews, it's important to focus on a few key areas. First, carefully analyze the problem constraints. For example, if the maximum array size is 10 to the power of 4, brute force methods are likely to time out. Understanding these limitations will help you decide whether to use a brute force, greedy, or dynamic programming approach. Recognizing patterns is also crucial. Many subset problems share similar techniques, such as greedy selection, prefix sums, or frequency analysis. Being familiar with these patterns can speed up your problem-solving process. When discussing solutions, make sure to communicate trade-offs. For instance, you can compare time and space complexities or the difficulty of implementation between different approaches. This demonstrates a deeper understanding of the problem. Lastly, always test your solution thoroughly. Use small and edge case examples to simulate your algorithm and catch any logical errors before finalizing your implementation. This habit not only improves accuracy but also boosts your confidence in the solution. Now, let's explore related problems and alternative approaches. Similar problems you might encounter on LeetCode include split array into consecutive subsequences, partition labels, maximum number of events that can be attended, and single-threaded CPU. These problems share overlapping concepts or techniques, making them excellent practice. In terms of alternative approaches, a greedy strategy is a strong option. By focusing on removing the most frequent elements first, you can significantly reduce computational costs compared to brute force. A priority queue or sorting based on frequency is typically used, giving this method a time complexity of O(n*log n and a space complexity of O(n) for frequency storage. Another option is frequency-based counting, where you use a hash map to count frequencies and then sort them in descending order. While simpler to implement, this still involves sorting, which affects the overall time complexity. For more advanced variations, binary search with prefix sums can be effective. This is especially useful when exact thresholds need to be met, as it optimizes the search process. Each of these approaches offers different trade-offs, so selecting the right one depends on the problem constraints and requirements. Great work! To wrap up, we reviewed an efficient solution to problem number 1338 that leverages frequency sorting to minimize the array size. Remember to practice similar problems and refine your understanding of space and time optimization. Thanks for joining, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!